With the global population and consequently energy consumption both skyrocketing, carbon dioxide is now being produced and released into the atmosphere at a rate never before seen. If this issue is not addressed sooner rather than later, there will be dire consequences for the planet and its inhabitants, such as rising sea levels, ocean acidification, more frequent and severe weather, and dangerously polluted air in densely populated urban areas. Other more localized issues are also associated with our heavy reliance on fossil fuels, such as oil spills. Even if you choose to blatantly ignore the facts, at the end of the day, oil and natural gas resources are expected to be depleted within the next 50 to 70 years. Clearly, fossil fuels are not a sustainable energy source, and so it is important for alternatives such as wind power to become more widely implemented in the very near future. For our second-year applications project, we were tasked with designing a wind turbine subject to the following conditions: a horizontal axis rotating clockwise when viewing from the wind direction, maximum angular velocity not exceeding 3000 rpm, a maximum total mass of 400 grams. For a wind speed of 10 meters a second, the turbine is required to self-start. The maximum power coefficient should occur at a tip speed ratio between 3 and 8. The maximum diameter of the blades should not exceed 400 millimeters. The blade was to be tested at wind speeds of 6, 8, 10 and 12 meters a second. There was also the option of going for a less conventional, more innovative design. However, due to our limited knowledge of aerodynamics and structural dynamics, we opted for a more conservative two-blade design. This was also associated with an easier fabrication process.
The goal of the experiment was to maximize the power coefficient, which is the ratio of the power delivered by the wind turbine to the total power available in the swept area of the blade. We began our experiment by choosing our tip speed ratio, which is the ratio of the blade tip velocity to the incoming wind velocity. If the TSR is too low, the wind turbine would tend to slow and or stall to a higher TSR, and the turbine would spin very fast through turbulent air. Power would therefore not be optimally extracted from the wind. Moreover, it would be highly stressed at the risk of structural failure. Using empirical data, we finally settled for TSR of 4.5. We want to maximize the rotor torque at our design TSR. This would be obtained by maximizing the CL over CD ratios. Using the Airform Tools database, we then shortlisted the different types of airforms which might be suitable for our design. In the end, we chose Airform 6G6043 as it presented a good L over D ratio, good stow characteristics, and a desirable thickness. As the highest stress concentration was at the root of the blade, we decided to reinforce it by placing a thicker airform, NACA 2412. We found that the maximum lift was obtained at an angle of 8 degrees, but in order to avoid storm which might occur with the blade twisting, we chose an angle of 7 degrees. Due to the difference in the tangential velocity between the tip and the root of the blade, twist has to be applied. In order to determine the chord length and twist of the blade, we could use the Schmitz and Betz equation. We chose the Schmitz equations as it takes into account the rotational wake when airflow passes through the blade and is therefore more precise.
Now let's consider the structural analysis of our blade. The forces which are of interest are the aerodynamic loads and the inertial loads. Using the blade element momentum theory, the blade is discretized into 20 elements. One of such elements is shown above, where the corresponding loads are accumulated. The lift and drag were then calculated, and the aerodynamic force was obtained from their vector sum. We then calculated the centrifugal force experienced by each discrete element. Using Creo, we obtained these cross-sectional areas of the different elements, and therefore evaluated their centrifugal stress. The maximum centrifugal stress was found to be at the tip of the blade. Using a MATLAB script, we then evaluated the bending moments experienced by each element in the vertical and relative directions. We then calculated the stresses due to these bending moments, with the second moments of area found using Creo. The maximum stress was found to be at the root of the blade. This was then confirmed by a structural simulation performed in Creo, which indicated that the root was under the highest stress. The total stress experienced by the blade is then the sum of these stresses and the centrifugal stress. This was then compared to the yield stress of PMMA and was found to be reasonably lower. Finally, we calculated the tip deflections so as to make sure we didn't have excessive deflections of the tip, since this is the area with the highest centrifugal stress. The tip deflection was found to be 1.9 mm, which we agreed was a reasonable value. We decided to have a safety factor of 1.6.
To manufacture the hub, 4 methods were used in the workshop: turning, reaming, milling, and broaching. We started with a smooth cylinder of aluminium. The material was removed on one side of the block to ensure there was accurate positioning with the machine. The resulting cylinder was then reshaped to have a diameter of our hub by turning. The central hole that went through the cylinder was made using the reaming machine. Then we used a CNC vertical cutting tool to mill down the edges of the cylinder to form the hexagonal shape. After that, we used the coordinate input in this machine to drill holes onto the corresponding surfaces of the hexagon in order to reduce the weight of our hub and for the grub screws. Finally, we made the keyway by using broaching so that the hub could be mounted in the wind tunnel securely. The 2 blades and nose cone were manufactured using a 3D printer and were printed as one piece in ABS plastic. Due to printing limitations, the trailing edges were made artificially thicker. Therefore, the extra material was sanded off the turbine blade to match the shape we desired.
Praise the Lord.
Testing is conducted in the wind tunnel. The wind turbine is mounted on the shaft. Let's test on the wind speed 6, 8, 10, 12 meters per second. Since the diameter of the wind turbine is small, and it can now self-start on the wind speed 10 meters per second. A small touch is applied on the wind turbine to enable the turbine to start rotating. The wind turbine is allowed to spin freely until it registers its maximum angular velocity. The brake is applied manually until the wind turbine reaches minimum operating angular velocity. In terms of the results, there is no structural damage during the test, and as we can see in the figure CP against TSR, presenting the data in the third-order polynomial, the highest power coefficient is 0.088 with TSR 3.55 at the wind speed 12 meters per second. And the maximum power generated is 11.36 volts. The corresponding angular velocity for the maximum CP for each wind speed are all less than 3000 rpm. The power generated is not the same as per day, but can still light up an energy saving bulb. Optional values for TSR are less than design value 4.5. Maximum difference is but 1. An additional test is carried on to find out the self-start wind velocity, and the result is 16 meters per second.
The performance of the design was somewhat unsatisfactory. Several aspects of the design can be changed to improve its performance. First of all, the hub was made too big and too heavy. This affects the merit function that we're targeting, as well as its self-starting ability. To improve the performance, we need to be shortening the hub, as well as reducing its mass. Streamlining it would also help. The cord near the root was also made too long. It was originally designed that way to reduce drag, but this ended up increasing it. To address this issue, that section would need to be shortened and preferably adopt a circular profile with as small as a cross-sectional area as possible. There is also a visible bump near the root of the blade, and this jump had affected the performance dramatically. The blade's twist profile would need to be modified to remove this bump. Also, the quality of sanding, especially near the root, can be improved to further reduce drag on the blades. The tips were originally designed with the intention of rounding them up with a smooth profile. Further performance increase can be achieved by improving its design using some CFD software. We can also look at using a variation of aerofoil profiles along the blade rather than just one throughout the length of the blade.